Okay, so basically we've gone over position, velocity, and acceleration, and just how to get from one to another, and that's just done by derivatives and integrals. So, so the main reason why this video is going to be about acceleration, as you can see, is because if you go back to the beginning, we discussed the sum of the forces equals mass times acceleration. Literally, this is the whole course. The whole course. So, and I just want us to get this down real well before we dive into all these forces and whatnot. So yeah. So anyways, so acceleration, it's the derivative of velocity. So so really, I want to talk about certain scenarios where there's constant acceleration. So typically that happens in projectile motion, and if you look at projectile motion, let's say you just have a ball or just some object that's being thrown has been thrown already. If you do a free body diagram of it, you just have its weight in the end. And so if you have some of the forces in the y direction, that's going to equal mass times acceleration, which is going to equal mass times gravity. So masses cancel on both sides, so acceleration is equal to gravity. So I guess this points down. So so yeah, as you can see, this is a constant acceleration. G is just a constant number. Technically, as you get farther out and as you do like orbital mechanics, it's not going to be constant. But yeah, that's just that's something we'll save for later. So for a different day. So anyways. Okay, so what happens when you have a constant acceleration in the end? So you have, basically if you want to get your velocity as a function of time, then that's going to equal basically the integral of acceleration. So, and if it's constant, I'm just going to leave an a. So, and for the kinematic equations, you always have to, well, you don't assume a is constant, you just know that a is constant, and you can only use these equations. So if a is not constant, then you can't use any kinematic equations whatsoever. So anyways, so if we take the integral real quick, it's going to be a t, and then we have a plus c again, So what is that plus c? So what happens when we basically put t equal to 0? So we get v of 0 equals 0 plus c. So in the end, that's just really the initial velocity. So I'm going to call it v naught. So c is just equal to v naught in the end. So in the end, so you get one of the kinematic equations. So I'll write this as the second one. So the first one is the most well-known one, and I want to just have that as the first. So at and then plus v naught. So now I'm going to erase this. Okay, so what happens when we integrate even further than that? So s of t is then, or the position. So I could use an x or y as the same thing. S is just distance in general. So in the end, most of these will be in vector form, these equations, but technically you can just have x completely for the equation or y completely for the equation. So anyway, so s of t is just the integral of v of t respect of time. So if we plug in v of t then for constant acceleration, at plus v naught dt. So in the end, when you integrate if you use the power rule, this is going to be squared, and then you have to divide by 2. So it's really a half here, all right, s of t t squared plus v naught t. And we also have another plus c again. So, so what is this plus c again? So what happens when we plug in 0 for time? Well, this is just going to be 0. So you have 0 squared plus v naught times by 0, so 0 plus c. So since s of 0 is just s naught, c is just going to be s naught, just as v was, well, c for the velocity equation was v naught. So anyway, so now I'll write it over here. So s of t is then going to equal a half a, I'll write that a little bit better, a t squared plus v naught t plus s naught. So yeah, and if it helps out for you guys to read my handwriting, I always make my T's with a little curl. I do that now so that you can distinguish between a plus and a T. So just I don't know. I know my handwriting is terrible, but you know I'm good at what I do. So that's all that matters. That's all that matters. Okay, so now for the third kinematic equation, we're going to have to do a little bit of messing around with derivatives. So now if we have a is just a constant, really the definition of a is dv dt. So get into a d, and so really if we have ds just equals to ds. That's the same thing as ds over ds equals 1, like if you saw my unit videos, you know. So if we just multiply by 1 right here, it's just ds over ds, you know. They in the end cancel each other out. So so anyways, so now let's just multiply ds to this side. So a ds equals dv dt ds. So now what we can do is, since this is like being multiplied right here, we can switch these two. So now this is going to be ds dt dv. Well, what is this in the end? This is really just terrible circle. So this is literally just v, ds over dt. You know, the derivative of position with respect to time is velocity. So now that's really just v dv. So so I know this is not really formal, so but it works. So if you take the integral of both sides, the integral just really means just a summation of all of them, and that's just going to be equal to the integral of v dv. So in the end, when you integrate, you're going to be going from s1 to s2, and or actually, you know what, we'll do s naught, or you know, s initial, you know, s initial, s naught, the same thing. So and then s final, and we have v final, it's an f, and then v initial. So I just want to talk about this a little bit more before we begin. So of course, if a is constant, you can bring it out. So but so basically, what happens when we multiply mass on both sides? So in the end, you get mass times acceleration, ds equals, so this is the integral sign still. So let me just erase that. It's a terrible integral sign. Okay. So anyways, so then the integral of v dv, and then we have to multiply a mass also. So so in the end, then we're going to get really the integral of really our net force, which is going to be our, so F net, because that's equal to mass times acceleration, times by ds, but I'm going to call it ds instead of dx now. So, so this should just pop out at you. This is really just the definition of work. So, and then if you integrate this, then that's equal to m. So when you integrate, it's going to be v squared over 2. So I'm going to write the half on the outside, v squared. So final minus initial, final minus half m v I squared. So really, this is just the change in kinetic energy. So I'll talk a little bit more about energy later on, but basically, in the end, this is just a massless form of just energy conservation. So anyways, erase all that. So now, what if A is not a function of S or V or T or something? It's a constant. In the end, then we'll be able to take out A, and so we have A, the integral of ds, si, sf, and then this is just going to be, like I said, just a half, and then v v final squared minus v initial squared. So when you do this integral now, it's going to be a, and then s final minus s initial, which in the end is just a delta s. So so now we have to just multiply. So yeah, this is still equal to that. But yeah, so if we multiply 2 on both sides, then really this is all this is going to turn into is 2a delta s equals v final squared minus v initial squared. So add that to the other side, and we have our kinematic equation. So v final or v of t, same thing. So squared is then going to equal v initial squared plus 2a delta s. Again, we were able, this is a kinematic equation mainly because we were able to take out a. So if a is a function, we can't take it out. So erase some stuff. Okay, so I just want to talk about this a little longer. So you can actually do this integral so this is not a kinematic equation then. So it's not one of those guys. Just because it's a function of your acceleration's a function in the end. So so you can do this integral. So if a is a function of s, or you divide a to the other side, so you have ds still. So somehow that's a integral sign. So anyway, so if a is a function of velocity, then you can just do v over a of v then dv. Of course, a of v being in the denominator makes it not pretty at all, but it's an integral still, and you can still do it. So so yeah, so you can do this if you yeah, you can do this if it's non-constant acceleration. So, but it just has to be a function of your acceleration has to be a function of position, or has to be a function of velocity. So, okay, so I just cleaned it up a little bit, and I kept this because this is still very useful in probably like your higher level classes. But in general, if you're just taking like the basic physics one, just focus on these, and in particular, but just everyone focus on the first 3. The next two are they're out there, but they're not as used. So, but yeah. So anyways, so now for the fourth one, what we're going to do is we're going to combine 1 and 2 basically. So, and well, I guess for the fifth one, we're going to do the same thing again. So anyways, so now if we take 2, so really instead of writing v of t, I'm going to write vf. So that's our final velocity. And then so I'm going to subtract v naught to the other side. So minus v naught equals at. So now we can just plug this into here. So now s, final, s of t, s final. Then we're going to have basically a half on the outside, and then we have v final minus v naught, or I'm going to do v initial. So this should just be initial. So anyways, so then that's just a times t is we substitute vf minus v initial into here, but we're still left with another t multiplied right there. So, and we have plus f naught, or f initial, velocity initial times by time, and then plus s initial. So now subtract that over there. You're going to get delta s. So subtract that over to here. So and then now let's just add this to this basically. So now we're going to have a half, and then v final minus v initial plus 2v initial, just because we're almost essentially multiplying a 2 over 2 right here, and then times by time. So, and then that just turns out to be basically v final plus v initial over 2 times by t. So this is almost like the average velocity times by your time that you spent. So anyways, so that's the next one. So delta s is then going to equal v final minus v initial times by time over 2. So erase this real quick. It gets real slow. Now that's real quick. Okay, so now we're going to do the same thing, except for instead of solving for AT, we're going to solve for just V naught, or V initial. So V final equals A times by time, so your acceleration times by time, plus V initial. So subtract this to this side then. So we get V final minus A t equals v initial. So now we're going to plug this in for v naught, or v initial. So, and I'm just going to subtract this over right away too. So because it's really just delta s. Delta s, is the it's the same thing as s of t, and then you have plus s naught on this side, or s final, and then plus s initial on this side. So whenever you're dealing with this delta, it's always final minus initial. So always final minus initial. So just always remember that. So anyways, so then we have still a half a t squared. It's a t. And then we're going to have v final minus a t times by time. So so now plus. So now if we distribute that t, then we get delta s equals a half a t squared plus v final, it's supposed to be an f, times by your time minus a t squared. So essentially this is almost like an x, and this is like an x, a half x minus x gives you negative a half x. So, um, so when I say x, I'm not talking about like the x direction. You know, I'm just saying random variable, you know. So in the end, this is going to be v final. Get a little bit smaller. V final times by your time is then going to equal, or well, not equal. So like what I said, like I said earlier, when you add those, you get negative a half a t squared. So this is your final one then. So delta S equals v final and I need to either get a larger pad or just get better at writing. So it's a half a t squared. So I'm going to erase this real quick. Okay, so basically in the end, so basically if you look at all the variables that we're using basically delta S, time, acceleration, v final, and then v initial. So if you look at all 5 of these, because there's 5 of these anyways, you can see that each equation has one that's missing. So, and that's always the key to doing this. So all you have to do is be like, hey, what do I need to solve for, and what is not given? So what's not given entirely, and what's but like not what you're trying to solve for, you want to use that equation then. So if you look at this, you don't have v final. So v final, and if you look at this one, you don't have delta S. So now if you look at this one, you don't have time. If you look at this one, you don't have acceleration. If you don't look at this one, well, if you look at this one, please look at it. It's going to be v initial. So, and yeah, so that's just all the kinematic equations. So all 5. Basically, in the end, you're not going to be using these really ever, but it's good to have more tools in the toolbox than necessary. You don't want to be like, I don't know what to do anymore. Anyways, so you do have the kinematic equations right here, but then you also have these equations, which are just integrals that you have to do, and that's if your acceleration is not constant. So constant acceleration, your acceleration as a function. Okay, so before I completely end this video, I just want to say one thing. This is actually supposed to be a plus. So, if I can draw it as a plus. So, plus, yeah. So, yeah, so if you caught that, good for you. Good for you. You're learning.